Hello to all physics enthusiasts and fans of physical experiments. I'm Andrei Shetnikov, and today we're going to tackle a problem that is more of a physics-mathematics nature, but it's very beautiful. And I wanted to introduce you to these beauties. Unfortunately, I won't have any live experiments this time, but nevertheless, I have prepared a simulation in live physics. And the problem is formulated as follows. Imagine that a jokester takes off upwards, and at the highest point, it explodes like a firework. It flew in all directions, these little burning particles, and at the same time, they are also falling down. And we ended up with an area where all this stuff happened, and outside. Accordingly, not a single burning particle reached the target. And the task requires us to find the boundary of this area. And I'll start with a simulation in live physics so that you can grasp the concept more quickly. And on the first run, I turned off gravity, and the particles fly outwards at equal speeds in all directions from the point of launch, so they are all the time. In our picture, they lie on a circle, and in the three-dimensional case, they lie on a sphere. I'll be talking about the circle for simplicity. And in the second trial, I turn on gravity. And now each individual particle is flying along a parabola. But when we look at all the particles together, we see that they are again lying on a circle. This circle expands at a constant speed, and it falls down with a constant acceleration g. And in this picture, the boundary separating the two areas has been drawn. We see that this is most likely a parabola, but in 3 dimensions, it's a paraboloid of revolution. And there's even a suspicion that the particles flew out from the focus of this paraboloid. But all of this, of course, still needs to be proven. But there are different proofs here. Relying on the properties of the envelope with differentiation and integration. But I wanted to find a proof that, first of all, relied solely on elementary geometry, and trigonometry, and secondly, was physically meaningful and useful. And now we will look for such a proof. Let's consider it with you. And for this purpose, I will launch all the particles again, but this time along the drawn trajectories. And I will wait for the moment when one of the particles, for example this one, touches the outer envelope. Here is its trajectory, and let's say it flew out with some speed v. When the particle touched the envelope, time had passed, and the center of the circle, during this time, it fell a distance of gt2 at a 2, while the particle flew away from this center a distance of vt. And the direction of this flight is determined by the direction of the initial velocity. Notice that the current velocity of the particle is directed tangentially to the envelope, which means it is perpendicular to the radius. Let's denote the launch angle of the particle as a. Then the components of the initial velocity will be v, sin, a, and v, cos, a. The horizontal component of velocity does not change over time, so at time t, it will also be equal to v, cos, up. But the vertical component of velocity changes with acceleration g, and at time t, it will be equal to v, ist in sin. A is the initial component, minus gt. Let's note that now all the angles are equal to r. By linking both components of velocity together, we get that v, cos, equals v sin r minus gt multiplied by the tangent of r. From here we can express the. And please do these calculations yourself. And then we will find that t equals v divided by g times the sine of alpha. Let's move on to the equation that interests us, the envelope. During time t, the particle will travel a horizontal distance of vt times the cosine of alpha. And if we substitute here the expression already found for t, we get v squared divided by g and multiplied by the cotangent. Alpha. Vertically, the particle will rise to a height of vt times the sine of alpha due to its initial velocity, and because of the acceleration g, it will drop by gt squared over 2. And again, if we substitute t here, and do all the calculations, we will get v, or squared, divided by 2g and multiplied by the bracket. 1 minus the cotangent squared of alpha. We just need to express the cotangent of alpha in terms of x and substitute it into weak. After which we find that y equals v squared divided by 2g minus gx squared divided by 2v squared. So the envelope is indeed a parabola. It's called the safety parabola. We found its equation and solved the problem. And someone might ask, what's the point of these kinds of problems? And I will answer this question like this. When high school students in a physics and math class tackle these kinds of problems, they struggle. They find their own solutions through complicated methods, and then they see the simple solution. Or maybe someone arrives at it on their own. Simple and beautiful. Well, in any case, some of them are touched by this beauty. And so, being touched by such beauty, people become true physicists, because physics is inseparable from this beauty. And now you can leave your comments under this video. Thank you for your attention, and see you next time.